Either I can continue with the lectures and start talking about multi-class classification, or just do a review of the first half of the semester. How many people say multi-class classification? So, how many people, just so that I know that you heard my question, how many people say review? Excellent. Okay. Okay, so that makes my life easier. I have no slides. I have posted a sample midterm, a list of questions. This is not a sample midterm. It's not going to be this long. Just a list of questions on the website. Take a look at it. You should be able to do it. And really, most of it is questions that are either directly related to what we've seen in class, or exactly what we've seen in class, or related to what we've seen in homeworks. Or some questions that I occasionally have in my slides, which I leave as exercises. I figure those could make good exam questions, maybe. So, a few announcements before we get into the review. Homework 3 was due yesterday. 3 or 4? 3 was due yesterday, and you still have until midnight to submit it. At some point past midnight or early tomorrow morning, I'll put up the solutions for the homework so that you can take a look at it. I've spoken to many of you through office hours and emails and stuff, and what I thought was going to be a very difficult homework seems like it wasn't. It was good. Okay.
Who told you it wasn't?
Oh, that's the feeling I got.
Where is the mole? Like,
so the idea being that all the questions I got were very good ones. I don't really care so much that you get the answer right as much as you get the way of thinking right. And as far as that is concerned, I'm happy. Reminder, there's a midterm on Wednesday. Yes. Yeah, I know. It's a closed book exam. You have basically the entire length of the class. Please show up a little bit early, just so that we get started on time. Any questions about the midterm itself? Yes?
Can we bring a calculator?
You won't need one. I'll make sure that you won't have to have any.
Well, like for MCP, there's a bunch of logs.
Yeah, I'll make sure that the numbers work out well. You won't need a calculator or a book or a computer or anything. Just bring a bunch of pens.
So should it be the case that we pretty much memorize all the equations to be able to decide?
You shouldn't. I don't want you to memorize equations. No, I don't want you to memorize equations. Even I don't remember them. You should be able to prove things. You should be able to define things. For example, the Occam's razor bound, m greater than 1 over epsilon times something. I don't want you to memorize stuff. I want you to get a flavor of what it is. What's going on in that expression? Why are the different terms there? Rather than what is. How do you do agnostic learning with VC dimensions? There is 8 times VC times 1 over something. It doesn't matter. Don't memorize stuff, but you should be able to prove things.
So, for instance, in a question where we maybe prove the mistake bound, then would you say give us the equation, and then we'd say how do we go about proving this?
Let's see. If I ask you to prove anything, I'll actually walk you through the proof. I won't ask you to prove something egregiously bad.
So you won't just, like in the list of possible questions, you won't just say something like proof perceptron converges?
Yeah, that was because I didn't want to write down the whole thing.
Okay, so that's not a question we'd expect to see.
No, if you see that question, you'll see a much more detailed version where you'll go through the steps.
Okay.
I mean, that also makes grading easier, because I can give partial credit instead of saying prove Novikov's bound, and then you write like 3 pages of a story, and how do I know what to do? So Before we get into the other midterm related stuff, I've updated the timeline a little bit of the lectures. So, the one thing that will probably affect you is I've given you another week or so for your intermediate project report, which I thought was due right after the spring break, and that seems like it's too early. So I've extended it by a week. Take a look at it and see if you're happy with it, and let me know. I'm not going to change it anyway. That's the set of announcements. If we can get back to midterm mode if there are any questions or anything. Otherwise, I've also put up a review document on the website. So it's basically it's if I understand right, it's a list of titles of all the slides, effectively. It's a list of things that you should know or be comfortable with at this point. And my plan now is to roughly go over a document that's like that. So I'll give you another choice. Either we can do that, just a review of the entire half semester, or we can pick some questions from the sample midterm and try to work them out on the chalkboard. And try to, meaning it doesn't have to necessarily be me doing the work. Who wants to do, let's do a review first. Just an overview of a lot of things. So, yeah, we started on the semester talking about what is machine learning, and for the entire duration of this time we've been talking about supervised learning. So let's see. Right. So we've been in this. If I write here, can you see how badly does this block you? That's my foot. About here? Okay, that doesn't give me much.
Usually people write on that board and just.
Yeah. Okay, so we've talked about supervised learning. Everything that we've seen so far has been supervised learning. And in terms of the core ideas that are involved, we've talked about instances, instance spaces, which are simply the set of examples, and labels. Nearly everything that we have seen so far has been binary classification. The labels have always been +1 and -1. The instances have almost always been high-dimensional vectors, effectively, even in the case of decision trees. So I've called these vectors feature vectors, I've called them attributes, and every example can be represented as a feature vector. And the important thing that we've seen is, so we have instances and labels, and we have concepts. A concept is a function that we are not aware of, and it comes from a set of functions called the concept set, concept class. And typically I've used the letter F to denote concepts. All we have in the supervised setting is a set of instances and this function F applied to each one. So we have an xi that comes from this set paired with its label. So training examples look like this. And we have a finite set of them. Our goal is to find an approximation of this function. And to do that, we will search over something called the hypothesis space. The hypothesis space is a set of functions that our learning algorithm tries to look for a function. And it finds something, we'll call it h, a function h. And our hope in everything that we have done so far, and in fact even from now, coming up, is that this function h is close to the function f. The hypothesis is in some notion of closeness, close to the function, yes.
Hypothesis is a bunch of different types of functions.
Hypothesis space is a set of functions and hypothesis is a single one.
So concept is one particular set of functions which is
Yes.
defined by a formula.
Yes.
And hypothesis can be different concepts within that space.
So,
And thus hypothesis.
So there is a set of functions called the concept class, or the concept set, and f is an element, a single element here. There is possibly another set called the hypothesis class, and h is probably a function inside this. There is nothing that we typically have no idea what the concept class is. And we hope that these two have a large enough overlap that the concept class, the hypothesis class contains the true concept. This is it, yes.
And this is agnostic when
In the most general case, it is agnostic. We can move these two sets around so that one contains the other. The hypothesis class contains the other. So this is a general setup for supervised learning. Yes.
Can you take one small classification task example and I'll give them and tell us the difference between what a concept
Sure.
is like.
Let's work out an example. So suppose you have a spam detection. My goal is to build a spam detector, and I can produce examples of emails with a label spam or not spam, and the label is given by people. Right? You click your, you give a feedback. Internally, you have some function in your mind. Maybe it's a function. So internally, you have some way of deciding whether an email is spam or not. I have no idea what happens internally within each of us. So the set of concepts is the concept, single concept function is the function that we are using internally to decide whether an email is spam or not. A hypothesis is the classifier that we produce to mimic the concept. Another word that I'll use interchangeably with hypothesis is the classifier. Okay?
Yeah.
And yeah, feel free to interrupt me. I want this to be a discussion. I don't necessarily have to go over the entire review. I spent the semester doing it. So the idea is, we clarify the foundations. Yes.
And this is only for batch learning, right? Online learning doesn't actually develop a hypothesis?
Not explicitly, but there is a set of functions that you have to commit to. There is a hypothesis class. The difference between batch learning and online learning is that are the examples given to you upfront or not? And the difference is in the way the learning algorithm produces a function. But end of the day, the learning algorithm still searches over a set of functions, whether it's online or batch.
So for perceptron, what would the hypothesis be?
The hypothesis class is a set of linear threshold units. No matter what you do, the perceptron will only get you a line. Right?
Oh, right. So each line is
It's a different hypothesis. Yes, exactly.
That formulation is called the concept.
The true
The
function.
W transpose X.
That is
the
a
concept.
hypothesis.
Yeah.
The true concept is a function that we never see.
So concept is always in terms of true hypothesis.
The concept is a hypothetical function. We never get to see it. The hypothesis is our estimate of the concept. Okay, let's move on. The first thing that we saw in this game is what's a learning algorithm? A learning algorithm is an algorithm that is given some data and produces a hypothesis. And at this level of abstraction, I don't care what it does internally. It produces a hypothesis, it can do whatever it wants. But already there seems to be a problem. And this is how we started the semester. The problem is that the number of functions, the number of Boolean functions is an unreasonable one. How many Boolean functions are there if you have n features? Is it 2 power n? I hear 2 power n. Right, yes. So this is the number of Boolean functions, and you should be able to prove this. It's not a terribly complicated thing to prove, but really this is an unreasonable number of functions. So the problem of learning is how do we concoct a search strategy that can explore this search space. And effectively the only answer that we know to this question is you don't search through this entire space. You try to find a restricted version of the hypothesis class and limit your search to that. And we've seen multiple examples of how this happens. So, any questions about this? Okay, so let's move on. The primary questions that you will have to deal with, and this is not for the midterm, but generally when you are building this, using this kind of stuff for anything out in the wild, is there are 3 important questions. One, how do you select your set of hypothesis classes? Or how do you select your hypothesis class? Why should you pick a linear threshold unit over a decision tree? Second question, so that's which hypothesis class? The second question is, okay, this is a hypothesis class, which learning algorithm should I use? But actually no, that's not the second question, that's maybe the third or fourth question. The second question is, what is your instance space? How do you represent? So the second question is representation. In other words, what are good features? And in your homework 1, you played with this question. Why should you choose this set of features rather than something else? Given a representation, another question is how do you actually learn? What's the learning algorithm? And the learning, under this question, many other questions are hidden. The primary one being, what is a good protocol for learning? Should it be online? Should it be batch? Should it be supervised? Should it be unsupervised, active? And you have multiple choices to make here. And let's, again, since we are restricted to supervised learning, by the way, I just noticed that this is rather light. Can you guys at the end see what's written on the whiteboard, or should?
You're okay.
Okay. So, the question is, how do you learn? There are many learning algorithms. Why should you pick a decision, the ID3 algorithm over, say, boosting? And one answer to that is that you really need to understand what is the strength and weakness of each learning algorithm, and which circumstance, or what are the assumptions that you have about your data that make you choose one learning algorithm over another. And the only way you make this decision is you need to understand what's the learning algorithm doing. Certain learning algorithms favor certain situations. For example, the Winnow algorithm is much better if you have very few relevant features. So if you believe that your data has very few relevant features, you're better off using a multiplicative update. The decision tree algorithm can learn arbitrary Boolean functions. If you believe that your function class is rather complicated, or the concept is rather complicated, then you might think of using a decision tree.
So you said Winnow works well when you have few relevant features among many features?
Yes.
Winnow.
Yes. When you have millions of features and only a few of them are relevant in the true concept.
Okay.
So you're making an assumption about the true concept here. And so this is something that an intuition that you'll have to build up in some sense, but there are theorems to help you build an intuition. The other answer, which is kind of rather lame, is I will use a certain learning algorithm because I have the code for it. Sadly, that ends up happening a lot more than most people would admit, because as the learning algorithms get more complicated, they end up being optimization problems, and nobody wants to write an optimizer every single time. So you write it once and you use it wherever you want. But that's a bad reason to do something. Okay, so given the situation, that's not good. Okay. Given the situation, now let's think about the different algorithms that we have seen. The first thing that we saw in the class was the decision tree. Now, the decision tree is not just a learning algorithm, but it's a way to represent data. So, and you need to know what a decision tree is. It's a tree. The nodes in the tree are, in some sense, features. Actually, they're tests for features. They're little functions that say, is this feature taking this value? Is it windy? Is it raining? And so on. So each node is a test, and for every outcome of that test, you have an edge. So you get something like so on. You have multiple outcomes for every test, and each outcome corresponds to an edge, and at the bottom of it, the leaves are always the outputs, the labels. Okay, so this can represent any data, and what you need to know about decision trees is that you can represent any Boolean function as a decision tree. You should be able to write down Boolean functions as decision trees. And the other thing that's important when it comes to decision trees is how do you predict using a decision tree? Given a new example, you need to basically apply the test all the way from the top, go down and reach a leaf. Whatever label is at the leaf, that's the label you're going to assign. There are a lot of tricks that you need to use to deal with real life data. One of them is probably the most commonly used one is how do you deal with continuous valued features. Here, the number of edges is equal to the number of outcomes that these tests can take. So you can't say, you can't have wind speed and then 0.1, 0.11, and so on. That's a ridiculous way of thinking things. So so there are a few standard tricks to deal with continuous valued features. One of them is to define little functions on them. Is the wind speed greater than half, or is wind speed between 0.3 and 0.33, and so on. And that way you get a finite number of branches. So the other thing that you need to know is I mentioned the expressivity of decision trees, arbitrary Boolean functions. But what are they functions of? They are functions of whatever tests you have here and the value. So day of week equals Monday. So that will be the Boolean in this thing. And this is something I'm going to keep saying multiple times today. Here's the first one. You should know how to count decision trees. How to count the number of decision trees. How many decision trees exist if you have n Boolean features? What can decision trees represent?
Functions.
Who said something? Yes.
Functions.
Which many decision trees are there if you have n?
2 to the 2 to the n.
Yes. So you can, so in some sense, you might have seen this multiple times in your homeworks as well. We'll keep counting the number of hypotheses in a hypothesis space, and that lets us specify how difficult or easy the learning can be. Okay, speaking of learning, we looked at an algorithm for learning decision trees, the ID3 algorithm. And you should understand what is entropy, what is information gain, and how to select the next attribute based on information gain. I made you work through some examples in your homework for this, and you might want to take a look at that again. And we can, if you have any questions, I'll be happy to answer them even now.
Missing values in decision tree.
Missing values in decision trees. How do you deal with missing values in decision trees?
The most common label at that level, like if you,
What if you do not have the day of the week? So let's say you have an example, windy equals yes, and that's it.
the most, oh, okay.
Only one of the weeks out there.
And you don't, let's say, so this is your full example. This is your example. I don't know the day of the week, but I know it's windy. Should I, what was it? Should I play golf or not? Yes.
It depends on how deep the tree is, but if the tree isn't very deep, you could just look at all the possible leaves and have them vote.
Okay, how do you train in this situation? What if your training set consists of examples with occasional holes?
The most common answer in the gaming example at that level, like all of the examples that have yes, you split them, take the majority of all the remaining ones.
So, what do you need for the ID3 algorithm? The ID3 algorithm effectively requires you to calculate entropy. That's all you need. But you need to be able to calculate the entropy for each, or the information gain for each attribute. So, you need the entropy for various splits of the data. So, one way is not the most common answer, you can fill up the most common day of the week. So, you have other examples, right? You can fill in, let's say you have 10 examples. All of them are fully instantiated except for one. And what you could do is, for the last one, take the most common day of the week. Just why? Why is that a reasonable thing? Because you believe your data comes from some reasonable distribution, and that's one answer. Another way of doing this is not to give this a particular label, say Tuesday, but instead give it fractional labels. In other words, you're going to create 7 examples here. I should have chosen, let's say, instead of day of the week, let's say it is. Yeah. Because I don't want to write 7 things. What you could do is create 2 examples out of it. The day is Wednesday and windy is true, but it's not a full true, it's a half true, because, or let's say in your training data, you've noticed that windy is true occurs 40 times and windy equals false occurs 800 times. One way of completing this example is to say that the windy feature will always be true, will always be false, because false is the most frequent one. That's option 1. Another way of dealing with this is all we need from this feature is to be able to count how many times it occurs. So let's just add a fractional label. I don't know the label to this. So let me pretend that this one occurs, this is I can't calculate these percentages. So let's say this is 10 and 90. Let me pretend that this is true 10% of the times and false 90% of the time. So I'm going to create a fractional example. What that means is I'll just change my counts by making this 10.1 and this is 91.
This is completely impractical.
Why?
Well, because when you have lots of features, the tree is exponentially big, and the training suddenly becomes exponential.
So no, you're just fixing the counts here.
Yeah, but still, the training becomes exponential because suddenly, I give an example, propagates in multiple paths.
You don't keep doing that every time. Every time you. So what is the interface for the ID3 algorithm? All you need is to count how many times each feature occurs with a certain label, right? So windy equals true correlates with a certain label 10 times. Say should play golf equals true 10 times.
Yeah, at that particular node. But when you come down to the bottom,
Yes.
you will need to take the 10%.
No, but ID3, remember ID3 is a greedy algorithm. So you just do one shot and you're done.
Yeah, you do one shot, but the point is that example will propagate multiple paths down to the leaves.
No.
When you will decide for the label at the bottom of the tree, you will need to consider all the examples that have non-zero
No.
probability.
You don't do that. What you do is you change the example once before doing anything. When the example comes in, you just give it a fractional label. Give the missing feature a fractional label and just stop. Because at prediction time, you may have to revert to this. Yeah, you're right. At prediction time, you may have to revert to giving it the most frequent label because that's what will matter. At training time, since you only care about counts for the entropies, you can change the counts by giving it the count of people. So we have, remember, for this corresponds to, let's say, a label. At training time, you'll have the true label. Let's say this corresponds to a label yes. What you'll say is, this example maps to, and let's say windy equals true maps to 10 yeses and false maps to 90 yeses. Okay? You don't want to skew the probabilities. So P yes equals 0.1. Okay? You keep the same probability and just change the count. So effectively, you're ignoring that data point. It's equivalent to saying you're ignoring the data point while training. You don't seem convinced. Yes.
So when we count 10, 90, is this at the constraint of day equals Wednesday or the whole data set?
It depends on which level of the learning you are at. So let's say at the top, it's at the whole data set. Yes.
Would it be a bad idea just to consider not having a label or data for that as another branch?
Say that again.
So if you don't know it's windy or not, then you could have that be a branch. So you'd have true, false, and we don't know.
Oh, that's basically, so effectively what you're doing is creating a new label, creating a new value for that feature. So your features are no longer binary, which is another way of doing it, but the problem with that is you're losing information. It can be done, but then you're creating artificial partitions of your instance space, which do not necessarily exist. Because a windy is a Boolean thing, either it is windy or not. You not knowing whether it's windy or not should not affect whether you should play golf. In an ideal world it will, but it should not affect your classifier's decision. Right? So that's a less than optimal strategy.
It'll remove the requirement to make assumptions during the test.
Yes, that is true. But then it will also create artificial partitions of the instance space which do not exist. So, okay, let's move on because I've got 3 pages of notes I wanted to cover and they are about at line 5. So, the one thing that you should know, absolutely, so there are no clearly good answers for dealing with missing features. What I would do if I had to deal with this problem in practice is just take the most frequent label, most frequent value of a feature. Why? Because again, it's just easier to implement and it does reasonably well, if at all I'm using this.
So still affect the level you're at or the overall training set?
I'll just first do a pre-processing of the training set add the missing features, and then use what I already have. So, one thing that you should know is how do you deal with overfitting when it comes to decision trees? Because there are various tricks that we looked at for dealing with overfitting. Why would decision trees overfit?
You can memorize the entire data set if you encode it all.
You will memorize the entire data set. So the decision tree is a consistent learner. It will always produce a function. If your training set does not have noise that renders it impossible to produce a decision tree, your learning algorithm will produce a decision tree that's consistent with it. Which means you will memorize even errors in the data. So how do you deal with it?
Stop growing your tree at a certain level.
Stop growing your tree. The problem is that the tree can get arbitrarily complex. And this was the first instance of Occam's razor that we saw, if you think about it. The decision tree is a consistent learner. And the problem is that we are allowing an arbitrarily large search space because we are letting the trees grow wild. So if you decide that my trees should be no larger than a certain depth, you are committing to a smaller hypothesis class. Again, the point about counting the size of a hypothesis class or measuring the size of a hypothesis class becomes important. There are fewer decision trees with a depth limit of 10 than there are arbitrary depth limit. So this is the first instance that we saw of Occam's razor. And I might have even mentioned it in class, but I might have just glossed over this point. So another thing about decision tree, the ID3 algorithm, if you think about it, information gain is a way of asking what's the most informative feature to predict a certain data set, to predict a label for a certain data set. That's how you find the top of the tree, right? So if your data set has 1 million features and only 3 of them are relevant, ID3 will do a reasonable job because it will find the features that are informative and it will ignore the bad ones. Because once it reaches a point where all the examples at a certain level have the same label, it will just use that label there. There's no more growth of the tree beyond that. So ID3 is an algorithm that can function reasonably well when there are when the number of relevant features is not as much as the number of features. So that's a big strength. One weakness of decision tree is that you're growing decision trees, so you're learning arbitrarily complex functions. And if you think about what we've seen since this class, since we saw decision trees, if you allow your learner to grow arbitrarily complex functions, it probably will. And there is no good reason to fit the noise in the data. So decision trees you need to have explicitly try to avoid overfitting. Questions about decision trees? Okay, the next thing that we saw after that is we went to nearest neighbors. Nearest neighbors is a completely different style of learning. The nearest neighbors classifier does not really have any learning. You're given a data set, done. Learning's over. Because there's nothing to do while learning. Most of the heavy lifting is done during prediction. So why whiteboards have shown up in most classrooms. So the nearest neighbor classifier is an example of an instance-based learner. And the idea being that you remember all the training set, and at prediction time, all you do is, well, it's not all you do, it's not trivial, but you find the nearest neighbors of your test example, and if you do something with that, the list set of nearest neighbors, you produce a label for that. The simplest example of a nearest neighbor learning, of a nearest neighbor classifier, is the one nearest neighbor. You find the closest training point, look at its label, and say that the test point will have this label. K nearest neighbors is a slightly more sophisticated version of this. You find not one but the K nearest neighbors, and maybe take the majority label. So, what do you need to define a nearest neighbors classifier? What do you need to write down?
Distance.
The distance. So there are different ways of measuring distance, and you need to know what different distance measures are. And most of the time, almost every time when people say nearest neighbors classifier, they assume the distance is the Euclidean distance. Why? Because it's just easier to reason about. How do you deal with categorical features? The Hamming distance. Another way of thinking about the Hamming distance is effectively it's an encoding of the categorical features in an n-dimensional space. So if you have a feature like, let's say, day of the week, Monday, I encode it as seven features. Only one of them is 1. And Tuesday will be, and so on. The Hamming distance between these two is 2. Well, you can normalize it and make it a 1. The Hamming distance between these two categories is also 1. So the Hamming distance is, you can think of it as applying a distance metric to an encoding of the categorical features. So what should you know about the nearest neighbors classifier? One is, how do you choose K? What happens when K is the size of the training set? K is an input to the program, right? K is a hyperparameter. So every learning algorithm typically has a hyperparameter. We didn't have any for the ID3 algorithm. We could have had a hyperparameter in the form of the depth, the limit, the depth limit. If I decide that the trees should be no deeper than 5 nodes, or 6 nodes, or 17 nodes, that's a hyperparameter. For K nearest neighbors, the hyperparameter is K. So you need to, how do you choose hyperparameters in the same way, instead of trying out everything? Is there a way of doing that?
There was something about your data.
That's one thing. But really, we looked at this idea called validation. You have a training set, you split it into you keep a little bit aside, and you pick a K, fit your, well, in this case, training is trivial, and then see how well this particular algorithm, this particular model does on the held out set, and try that for different Ks, find one that works for you. A more grown-up version of this is called cross-validation, and you'll be looking at that in your next homework, which by the way will be released today, because you've been crying out for homeworks. So, from a practical point of view, one thing that you should understand, and this is really important when you do nearest neighbors, is you're applying a distance metric, right? So it's what can mess up a K nearest neighbors or one nearest neighbors classifier really badly? If I give you a training set, worse than that, it can render learning impossible. Suppose,
You consider the values that you use.
Yes. So some features might be in the order of 1 million. Another set of features, which let's say these are the most important features, and these other features might be order of 0.001. And the large features are irrelevant. But distances will be dominated by the large features. Right? So an important thing that you need to do when it comes to practically using k-nearest neighbors or 1 nearest neighbors or any variant of these is to think about feature normalization. And really there are no, or at least to my knowledge, I can't think of any necessarily great ways of doing this. There are standard ways of doing this, and I can tell you what it is. You just take every column of your data, every column is all the values that this feature takes, let's say, and center it, put it on, give it a 0 mean and unit standard deviation. And that makes sure that all your data, basically all the features are equally large. It works, well it may not work, but it's done.
We make it centered mean or we divide it by the max?
That's another way of doing it, but
if we center mean, then the ranges remain.
no, you center it and then divide by the standard deviation. So if you have a feature, xi, let's say, you have multiple values for it. So that it lies on, it's centered and they have the same magnitude, roughly. And this is important from a practical point of view. Another thing that you should be able to reason about is what is the decision boundary of nearest neighbors classifiers. And these are the Voronoi diagrams that we've all seen and loved so much. So you should be able to draw Voronoi diagrams for at least Euclidean distances. And you should remember that the nearest neighbors don't necessarily produce linear classifiers. The decision boundary doesn't have to be a line. It can be rather complex shaped objects. So one advantage of the nearest neighbors is that it's rather simple. Really, I mean, you should be able to write a nearest neighbors classifier in 3rd grade. The other big advantage is it can represent arbitrarily complex functions because the decision boundaries are not linear. They can be really complicated objects. The problem with decision boundary is that storage could be an issue. You store the entire training set, and if your training set is the internet, then you might run into trouble. And another thing is prediction can take longer because prediction you need to find the nearest training point, which means you have to somehow iterate over the entire training point, training data, which means you have to come up with some fancy indexing techniques or something, or you have to do a linear search, which, as we are computer scientists, we know we never do it. So there's some indexing to be done. So you index your training set into, say, for example, a KD tree or something like that. Basically, you want to find points that are close by and find them fast, and without having to search over the entire training set. Another way of doing that is to live with approximations. You can say that I'm not, okay, it's okay if I miss a few training points. Let me find approximate nearest neighbors. And that's a huge area of research in itself. The other important thing, which is important enough that I should probably put it on the other board, is the curse of dimensionality. So we talked about overfitting. When it the curse of dimensionality is this argument that says that as your as the dimensionality of your instance space gets larger and larger, as your examples get, as the number of features gets larger, weird things happen. High dimensional space is a scary space. And we've seen, and with the class we saw multiple examples of how this manifests itself. One way of thinking about it is, as you go to higher dimensional spaces, most of the volume of a cube lies on near the edges. And that, if you think about it, is rather counterintuitive. And we saw an example of where we try to fit a ball inside a cube and ask for what fraction of the cube lies outside the ball. And as the dimensionality gets bigger, we see that that fraction gets closer to 1, which is rather unnerving. As far as the nearest neighbors classifier is concerned, because of dimensionality should means that distance, the notion of a neighborhood gets less and less well defined as the dimensionality gets larger. So your nearest neighbor might be really far away in higher dimensions, and the hope that the label of that far away point should match this test point is meaningless. So any finite set of samples will not really cover the space as your dimensionality gets larger. You just need to be aware of it and realize that this could be a problem that will affect you. And because of dimensionality is something that affects basically any classifier. Nothing we can do about it except understand that it exists and not just think twice before transferring intuitions from 2 or 3 dimensions to infinite dimensions. Okay, so that's all I have about nearest neighbors. Questions? Yes.
If you were to instead try to normalize through tweaking your distance metric, is that pretty much the same thing? Right?
It ends up being similar. It ends up being somewhat similar. Other questions? Right. The next thing that we saw after we looked at nearest neighbors classifier is we just took a brief excursion into this world of linear classifiers. And the point that you should realize is that we are basically stepping through different hypothesis spaces here. First, we considered the case when the hypothesis space is a set of decision trees. Then, for nearest neighbors, the hypothesis space is effectively any arbitrary function. The linear classifier takes you back down to a much smaller set of hypotheses, namely linear threshold units. A linear threshold unit is defined by given an example x, which is an n-dimensional vector. A linear threshold unit is defined by a weight vector w, which is in n dimensions, and a bias, which is a real. And a linear threshold unit is simply a classifier that looks like this. It's a classifier that takes the dot product of the weight vector and your input and compares it against the bias. If the dot product crosses the threshold, then you label it as a positive example. Otherwise, you call it a negative example. It's a rather simple class of functions, and you should understand the geometry of this class of functions. It's a linear threshold unit. In other words, in 2 dimensions, it's a line. In 3 dimensions, it's a plane. In n dimensions, it's a hyperplane. Yes.
What is there I don't know, does this mean anything in 1D? Like, what is a hyperplane in 1D?
Good question. What's a hyperplane? What's a line in 1 dimension? Point. It's a threshold, right? You just say it's greater than. I wish I had thought of that question. I would have put it in your exam. Yes, we can. Yes, we can. Yes.
So what's formally the hypothesis space of nearest neighbor? It's basically Rn.
It's basically no, hypothesis space is a set of functions.
Yeah.
So it's not Rn. It's
So it's all everything.
all functions.
Yeah,
It's
all
Rn to
Rn.
Rn to R or Rn to 0, 1. Yeah, it's crazy. So you should know the geometry of a linear threshold unit, and that's actually why the nearest neighbors tends to have somewhat dubious properties when it comes to learning theory, because you can represent arbitrary functions. The VC dimension of one nearest neighbors is infinite, and after rather a tedious session of trying to prove it, I'm convinced that the VC dimensions of k nearest neighbors is also infinite. So, which means you can represent any function. Which means to get the kind of epsilon delta bounds that we looked at in back learning, the number of examples you need to make that kind of a statement is infinite. So, then let's come back to linear threshold units, and we have 25 minutes, and oh well. So you should know the geometry of a linear. Do you have a question?
Yeah. So on the review, it asks there's a question regarding linear threshold units, and we're given some data. And for that question, are we just supposed to give a weight vector or something?
So weight and a bias.
Okay.
So the linear threshold unit is defined by W and V.
Okay. So just those two vectors.
Yes.
Okay.
So an important thing that you should try to, and this is not just for the exam but for life. Well, yeah, certain aspects of life, is the following point. What happens if you forget the bias? If you forget the bias, or let's say fix the bias to be 0. In 2 dimensions, the linear threshold unit, this function in 2 dimensions looks like x, let's call this x1 and x2. This is a different B. Asking for a line, some line, and you're saying everything in this region is positive, and everything on the other side is negative. Right? What happens when bias, in this case C, is 0? You are only restricting yourself to lines that go through the origin. Which means, if your data looks like you can't separate it. So, if the bias is fixed, and what happens when bias is not 0 but say 1? Is that, do you get the full expressivity? Do you get arbitrary lines by setting the bias to a non-zero constant? No. You're just shifting the center, exactly. So, it's very important to realize that the linear threshold unit is defined with both the W and the B. Do you have a question?
If you set your bias to exactly 1, then can't you rescale A and B to be a larger vector and then constantly?
Oh yeah, sure. You can do that for a fixed A and B. Or, yeah, you're right. If you, in fact, that's, so let's look at it algebraic. So you have AX plus B plus C greater than or equal to 0. I can divide everything by 3 and this works. But that means that this one has a certain, you are assuming something about the A's and the B's, or these things. Right? So you are rescaling, which means you are making an assumption about, in this case, not the norm, but it's okay to assume that the norm of the weight vector is 1. In fact, once we come to support vector machines, we'll do that very frequently. In fact, that's how we'll derive the learning algorithm for this. Because effectively, if you think about it, all we care about is not the actual magnitude of W transpose X, but only the sign of it. Or only the sign of W transpose X minus B. We don't care about the magnitude, so it's okay.
What was the linear threshold unit for a Boolean expression, like x1 or not x2?
X1 or not X2?
Yeah, that's one of the questions on the review.
Okay. So you have X1. So let me just work. So who can anyone answer this?
X1 minus.
How do you represent X1 or not X2 as a linear threshold unit?
X1 minus X2 greater than 1 or greater than 0.
X1 minus X, or effectively X1 greater than X2. Greater than equal to? Does this work?
Are we using zeros and ones or minus ones and ones?
Let's say zeros and ones. Does it work? How do you get it? How do you get it?
So for each literal, you're sort of treating it as, one value for that. So you sort of think of Boolean expression, and then ORs are, I got any one of these, so OR is just a plus.
Or is a plus.
And then ANDs are, just multiplication.
ANDs are like multiplications, but then you no longer remain linear. So, and how do you do x1 and x2? So, so x1 and
x1 plus x2 is equal to 3.
x1 plus x2 is greater than or equal to 2. So you change the bias. And in some sense, my preferred way of thinking about this is to plot this in 2 dimensions. Because we have 2 dimensions, you have 0, 0, right? x1 and x2, say if this is a 1, these 3 are zeros. Which means you need this line. And then figure out the equation of that line. 2 dimensions, it's easy. In 3 dimensions, I don't know how to plot it. So you have to kind of take the 2-dimensional thing and expand the intuition. So if you say that x1 and x2 and x3, that becomes x1 plus x2 plus x3 greater than or equal to 3 or 2.5 or 2 plus epsilon. Okay? In general, for OR, and the way you reason about this is, think about an AND requires both of these to be true. That's the bias. 2. OR requires even one of these if it's, even ignore the negation, even one of these if it's true, that's good enough. And because we are in the world of Booleans, if you have a function, if you have a Boolean x, that's represented by x, not x, equals 1 minus x. And you use this and you replace, every time you see a negation, you bring in a 1 minus thing, and then you cancel out the ones, constants to get a linear threshold. It's a fairly mechanical process. In fact, I know a guy who wrote a program that does this for Boolean functions, and it had some crazy recursion in it. In any case, so you should know how to represent functions as Boolean functions as linear threshold units. You should also know what can't be represented as linear threshold units. What's an example in 2 dimensions? Huh? No. I have a 2-dimensional function. What's a Boolean function that can't be represented as a XOR is one function. And speaking of the homework, you should know how to this trick about feature expansion or lifting, which can take functions that don't look linear, you map it to a different space, and suddenly you have it's linear in that different space. And we looked at an example in 1 dimension for this in the class, where you had function that looked like this in 1 dimension, pluses here and minuses here. So effectively this is the function, and you cannot plot a 1-dimensional line on this, a point that separates the pluses and the minus, and the way you deal with it is to map it to a 2-dimensional space by putting the pluses somewhere here and the minuses here. And then you can draw a line. And the mapping function to get you from here to here is some feature function that takes an input to, in this case, we've seen this in the class slides. You map every x to this 2-dimensional space, and here point data is linearly separate. Through the class, through the next half of the class, we'll be looking at this idea quite a bit more, especially when we talk about kernels. There's a way of computing these things without actually computing dot products in these higher dimensional spaces without actually drawing up the feature space. So, when we spoke about linear classifiers, we also talked about linear regression, and I spoke about this idea of minimizing error. I write down an error function as a function of the training set and your weight vector, and define learning as any algorithm that minimizes that error. And the algorithm that we saw in class was gradient descent and stochastic or incremental gradient descent. And that led to an interesting update rule called the Wittrow-Hoff rule. And what you should do is compare the update rule that you saw for the stochastic gradient descent with perceptron. They look somewhat similar. So I'm not going to talk about it much, and we'll be talking a lot about stochastic gradient descent in the second half of the semester. So let's get back to away from the linear classifiers and into this analysis of learning. We saw 2 different ways of thinking about analyzing learning. The question when it comes to analyzing learning is, what does learning mean? How do I know? Anyone can write an algorithm. How do I know that it's good? And the 2 dominant styles here are mistake-driven learning and PAP or batch learning. So you need to be able to think about what the differences between these 2 are. What is online learning? What is back learning? And online learning is the following setting. Or what's batch learning? Online versus batch. Online learning is the following setting. You are given an example. Your learning algorithm at all points maintains a hypothesis or some way of making a prediction. It gets a new example. It makes a prediction. And then the oracle gives it the true label of that point. At that point, the learning algorithm can actually check if there is a mistake. If there is a mistake, it can update its belief about the world and continue. And in the ideal setting, this is an infinite process, infinite loop. This keeps going. In practice, we don't have infinite data. As much as people might try to convince you about big data, it's still not infinite. So the game that we are playing in mistake-driven learning is to bound the number of mistakes. How do we know that the learning or can we say that this learning algorithm for this particular hypothesis space? So the mistake bound is a function of the learning algorithm and the hypothesis space, and it says, irrespective of what the sequence of examples that irrespective of the sequence of examples that shows up, my learning algorithm will not make more than these many mistakes after and after making those mistakes, you're done. And if that number is a polynomial in the complexity parameters, we'll call this algorithm a mistake-bound algorithm. We saw three examples of mistake-driven algorithms. One was this purely conceptual algorithm called the halving algorithm. And the halving algorithm has a mistake bound that is the log of the size of the hypothesis space. Once again, to understand the learning algorithm, we need to understand the set of functions it explores. So we need to understand the size of that function. So the complexity parameter, the important complexity parameter here is the size of the hypothesis space. And the halving algorithm is fantastic. It says the number of mistakes you'll make is only log of the size of hypothesis space. Unfortunately, it's an impractical algorithm to implement, except for the most trivial cases. So we won't be spending too much time on that. Another mistake-driven algorithm that we saw and spent a lot of time on is the perceptron algorithm. The perceptron algorithm learns a linear threshold unit, and it comes with a theorem. Every mistake-driven learning algorithm should come with a theorem. You need two things. You need an algorithm and a theorem. The algorithm produces the hypothesis. The theorem says that this algorithm is not valid. But for the perceptron, the theorem, which is called the Novikov bound, says that the number of mistakes that the learning algorithm will make, the perceptron algorithm will make, is no more than r square over gamma square. R is the farthest point, the distance of the farthest training point from the origin, and gamma is an interesting thing. It's called the margin. You should know what the margin is. You should be able to compute it for some tiny data set. And in some sense, so in fact, for example, here, for this data, I could have one hyperplane that's positive here, another one that's this way, and the margin in both cases is huge because the margin is tiny. The distance of the closest point, so the distance of this point from this line is very small. The largest margin that you get is a line that goes through the middle. It's equidistant from the positives and the negatives. So you should be able to compute this. In this case, I'm not going to spend time on that. But the Novikov bound says that the mistake bound theorem says that if the data is separable, linearly separable with a margin gamma, then the number of mistakes is no more than r square over gamma square. It's an important if. If the data set is not linearly separable, all bets are off. We also saw another algorithm called Winnow. Oh, but before that, we looked at different variants of the perceptron algorithm, and the important ones that I absolutely demand that you should know, irrespective of whether you want to learn it for the midterm or not, are the margin perceptron and, more importantly, the average perceptron. If you are ever implementing perceptron any time in life and you do not use the averaging trick, I'll find it. Another mistake-bound algorithm that we saw is Winnow. And the big difference between perceptron and Winnow is that perceptron makes additive updates. By the way, you should know the update rule for perceptron and Winnow. Perceptron makes additive updates. If it makes a mistake, it adds or subtracts to the weight vector. The Winnow algorithm multiplies or divides each weight, promotes or demotes features. If a positive example, if you make a mistake on a positive example, then your right hand side of, if you make a mistake on a positive feature, your right hand side is too low. So what you do is you promote all the features that are present in this example. You multiply each feature by 2 or some positive constant greater than 1. If you make a mistake on a negative example, you demote all the features that are relevant. The Winnow algorithm is an online learning algorithm. That's easy. It's also a mistake-bound algorithm, which means it comes with a theorem that says the number of mistakes the Winnow algorithm will make is O of what? If you have n-dimensional examples, some people come on. It's order of log n. So in the class we looked at the proof for k disjunctions, and it's order of k log n. So the Winnow algorithm will shine when number of relevant features is much smaller. When k is much smaller than n, then perceptron, you should be able to decide which algorithm to use. Why would you prefer Winnow over perceptron? Because you're making an assumption about the true concept. You're believing that the true concept is a sparse function, and so a multiplicative update with an whose complexity is only k log n is much better than an additive update, which is order of n divided by gamma squared. So the other thing you should know is what can the Winnow algorithm represent. So I'm not, given that there are only about 4 minutes left, I'm not going to talk about it. The algorithm that we covered in class cannot represent arbitrary Boolean functions because you're only multiplying and dividing, so you'll never get negatives. And there's a variant of this algorithm called the balanced Winnow, which can deal with it. And we briefly spoke about it in class, and you should be aware of it. Okay, so that's about the online learning part. The other bit that we covered is batch learning. And batch learning is distinctly a different beast from online learning. In batch learning, the setup is the following. You're given training examples, and these examples are drawn from a fixed but unknown distribution. Our goal is not to get low training error, but to hope to do well enough on future examples that are drawn from the same distribution. So this is an important assumption in batch learning, that the test and train distributions are the same. If you break that assumption, all theorems fall apart, and we come to this exciting new territory called domain adaptation. So we spoke about pack learning, and in pack learning there are 2 parameters. One is we give up all hope that we'll ever find a classifier, a hypothesis that's perfect. We can get an approximation of the true concept, and we want to say how close will this approximation be. This is your term epsilon in all the bounds. How close is the approximation of your, how close of an approximation is your hypothesis compared to the true concept. There's another term delta, and delta says, or 1 minus delta is your confidence in your learning algorithm that your algorithm will find such a good enough hypothesis with a low epsilon. So there is this epsilon and delta. These are the parameters to all the proofs that we looked at, and you should be able to define pack learning in terms of these things. And there's also efficient pack learning, which says that there is it's not just this hypothetical concept. You're able to produce an algorithm that can actually find a good enough hypothesis. We spoke about sample complexity and computational complexity of learners, which come from these 2 aspects. And we looked at Occam's razor. Since there's basically about 45 seconds left, I'm only going to list out the kind of things that we've looked at very quickly. And if there are questions, you can come to office hours or come talk to me. We looked at Occam's razor, and the assumption is that if you find a consistent hypothesis, then the number of, if you see these many examples, you can get epsilon delta bounds. Then there's agnostic learning, where even if the hypothesis, even if your learning algorithm is not consistent, even if you make errors on the training set, with certain conditions you can get epsilon delta bounds. All of these bounds depend on the size of the hypothesis space. Once again, the same thing comes up. To make any formal statement about learning, we are talking about the size of hypothesis spaces. We are counting the number of functions in a hypothesis space. This whole argument breaks down when we go to infinite hypothesis spaces, like linear threshold units. And to deal with that, we introduce this idea of Chartrand and VC dimensions. Effectively, the VC dimension is a surrogate for log of the size of the hypothesis space. And it shows up in all the bounds in place of the log size of hypothesis space. So you should know that the VC dimension of linear threshold units in D dimensions is D plus 1. You should be able to prove this statement for 2 dimensions for the plane, and we worked through this proof in the class. And the one last thing that I want to sort of mention is you should be able to make a qualitative analysis of these kinds of statements. This is a sample complexity bound, but what does it mean? If you have more than m examples, then with probability 1 minus delta, your learning algorithm will produce a hypothesis whose error is less than epsilon. And this term is polynomial in 1 over epsilon, log and 1 over delta, and depending on the size of h, it could be polynomial in the dimensionality. If it is polynomial in the dimensionality, then you call it pattern. You also see another term that says the error D, the true error. You should know the difference between true error and training error. Is no more than plus some term. And you should be able to interpret this kind of an expression. So this says the true error can be no more than the training error plus some deviation. Okay, I think I should stop because I'm at least 3 minutes past the time. And I'll see you guys on Wednesday. Please show up slightly early if you can. And bring enough pens for you and your neighbor.